Okay, so the trick for these guys is making sure that you get your selections done. Once you get your selections done, the rest of it should go pretty quickly. So all you were supposed to do, find all of your pairs. Well, first off, find mean and standard deviation of your original data, all of the possible pairs, mean of each of those pairs, make a dot, mean and standard deviation. So this is what you should have gotten. Your class average was 3.4 for the score with a standard deviation of 1.517. So that's the original data. Y'all okay with that? List one of our stats. And then for each of your samples, here are each of the means for those samples, taking the average of each of those pairs, and then graphing that. And for Part D was asking us to calculate how do they compare, and do you think this is an unbiased estimation of the population mean? So we found all of the possible samples of size 2. We've graphed them here. Now when I go through and I do that, did you get that your sample average was 3.4? So you're okay with that? How does that compare to what the overall actual average was? It's the exact same thing, right? So when it's talking about an unbiased estimator, what do you think bias is going to do to what you estimate your average to be? It's going to skew it. So what does that mean if I'm looking at the two values? Well, not the same. Okay? If something is biased, then that means that I'm pulling people so that it skews the results, and to skew means to grab and pull it in one direction or the other. So that means it's going to affect the average. So this should be the same thing. Now my standard deviation here is 0.876. How does that compare? It's smaller. Do you see the actual number that relates those two? Is that half? It's close. It's not half though. There is a relationship here, and this is what we're going to be looking at today, but it's not exactly the same. But you do see that when I start taking samples, my standard deviation decreases. So problem number 2 was asking us to do the exact same thing over again. So we still have my total class average of 3.4 and standard deviation of 1.517. But it's saying if I go up to a sample of size 3, what happens? So here are all of your samples of size 3, just like I had listed on the board. Each of their averages, and if I look at my sampling distribution here, do you see how if I compare this graph to this graph, they both go from 2 to 5, but on my second one, that's pulled in. So if I look at all of my possibilities here, and then all of my possibilities here, my graph itself has pulled in. The average of all of my samples of size 3 was still 3.4. Yes? So this is, what we're doing here is we're finding all samples of size 3, and then for that sample, adding them up, divided by 3. Okay, yes. So for the final mean and standard deviation, you can either plug this row here for B into your calculator and do one of our stats. Or for the mean, it's take all of these, that second row, add them all up and divide by 10. Okay? So what we should have seen here is by taking a larger sample, my graph of all the possible samples comes in. Comes in. The average should stay the same as what we started with. But if we look here, this standard deviation is 0.582. So it's still smaller than 1.517. How does it compare to the sample of size 2? It's smaller still. Okay? This is what we're looking at today, because with statistics normally isn't nice enough where we have every single thing that's possible. If I knew what the actual average was, I wouldn't need to take a sample. Do you understand what I'm talking about? The purpose of statistics, wait a minute. I think we said something over and over again. We said context, yes. Population is to something as sample is to something. Population is to parameter as sample is to statistics. This class is not called parameters. Do you get what I'm saying? This is not a parameters class. This is a statistics class. This is a class that's based on taking samples and going from a sample to try to figure out what's going on. So what this is talking about, this chapter, chapter 17, and actually the AP College Board actually looks at our chapter as an entire unit. So we're going to spend a little bit of time on it, make sure that we're set with it. But this is all about sampling distributions. What are all of the possible distributions of certain sample sizes? Now what's nice here is when we started with this problem, we only had a total of 5 things to go from, and an extremely tiny AP Statistics class. Teeny weeny, itsy bitsy. So it doesn't take too long to actually go through and write all of the possible combinations. But if I were to look at the senior class, how many are in your senior class? I think we 700, 750 something. If you were to do all possible combinations of size 2 out of 750, would you be willing to do that for me? What about size 3? Extra credit. No. Even with that, I'd be like, no, it's not worth it. Don't do that. So what we have to be able to do is we have to be able to say something based off of one sample and go from that to the whole population. And that is really the goal for this class, to be able to go from data to the world at large. Okay? That's what we're looking at for this chapter. So, the whole goal, what we're kind of taking this bridge right here. We're going from collecting data and understanding like what that data looks like, what that data means. Is it even something I can use? Is this stuff independent? Do I have some sort of a linkage going on? What's the probability supposed to be? And we're going to start moving this into the world at large, doing something called an inference. Inferences is about using statistics to try to make a statement about the whole entire population. You don't need to write that down. You don't need to write this down. Okay? And what we've seen, because that's exactly what we just did, is we saw all of these different samples, and from each of those different samples, you have different results. So if I were to take a sample of 20 seniors, and you were to take a sample of 20 seniors, and we were to look at their average GPAs, our samples are not necessarily going to have the same average GPA, because every sample varies just a little bit from here to there. And because each of those values vary, the statistic itself is a random variable. Random meaning, what does random mean? Kind of equal opportunity outcome, but more along the lines of we can't predict. Random means I cannot predict what's going to happen. A simple random sample is where every sample of size n has an equal opportunity to be selected. But random in and of itself is just saying I can't predict what's going to occur. And variable means something that changes. So a statistic is something that changes that we can't necessarily predict because each sample in and of itself changes. So if we think about it, my population is a big group, and from that group I take a single sample, and what I'm hoping is that sample is going to say something about the whole population. We take a sample to hopefully learn about the population, because there ain't no chance in heck I'm going to be able to get every single person. Very, very difficult. What do I call it if I got every single person? Census. Census. It is a census. Okay, now this is actually an old slide. This is something that we talked about almost at the very, very, very beginning. We said a parameter is something that describes the whole population. Either the proportion, like the proportion of men in the United States, the proportion of people with blue eyes in the United States, the proportion of people who are even better than that and have brown eyes in the United States. Whereas a statistic is what describes it for your sample. And we had S's and P's, so sample, statistics, population, parameter. You want to remember that. You also want to remember this table. You remember seeing this table? Back in the day, we had so much fun saying moo, not mu, not moo. Or that's pronounced P. I thought it was funny. Remember doing that? Huh? Yes. Yes. So it's yes, it is. It was in one of our flip books. Oh my gosh. So what we're getting down to right now is it's very, very, very important how you denote these things. If something is a statistic, which means it comes from a sample, the ones that right now we're going to be focusing on are Y or X bar, which is your average, versus P hat, which is a proportion. And their corresponding parameters, again, we're focusing on mu and P for an average and a proportion. Okay? So these are the two that we're going to be focusing on for this chapter. We'll spend one day on each of those. The problem is just what I said. Each sample can be different. That samples vary. And because of that, we've got to be careful, because whatever X bar, Y bar, whatever average I calculate from my sample might not be the exact same thing that I would calculate for the entire population. So I believe that's the white phone, third row down, third row in. It's a very pretty sound. It's very soothing. It's pretty. Because it flashed a little bit first before everybody turned around. Yeah. She's like, I can see sound. All right. It's okay. It's okay. So samples create statistics. Populations create parameters. Problem is, look at this. My samples can be all over the place. Did you guys catch that? One sample might be completely different from another. Some samples overlap. And each sample will have its own statistic. So we kind of have to think, how good is this statistic? Is this doing the job that I want it to do? Okay? So here we have two little setups, hey, words. And the words are actually given to you in your notes. Gasp, I gave this to you? Yes, I did. To the moon! All right, so you have numbers, two numbers for each of these problems that are underlined. What I'd like for you to do is I'd like you to tell me, of those underlined values, which is a parameter, which is a statistic. Simple, simple. Which one's a parameter? Which one's a statistic? Try to use the correct notation. You don't need to write out parameter equals statistic equals. All you have to do is talk about, am I dealing with proportions, or am I talking about averages? So is that a P hat, a mu, an X or Y bar? What is it? Go back to the chart. There you go. Which was already pointed out. You guys already have this in a flip book, so you will not be asking to write it down again for this next chapter. I'll give you your flip book after we've taken the next test. I don't want you guys having multiples of those floating around at the same time. Yeah. Should be. Yep, someone just flipped it over, see. Okay. So basically, like I said, we're dealing with means and proportions. So that's the first thing that you need to identify. What type of a number are you dealing with? And then you need to figure out, is it a sample or is it a population? Samples have the statistics, which are this first column here. Populations have parameters, which is the second column. That's how you denote the specific notation between them. All right, this shouldn't have been too complex. So if we're going back to this for problem number 1, which of those two numbers is the parameter? Which one about her? 41% is the parameter, because that's what I'm trying to estimate. I'm trying to figure out what actually will happen, whereas the statistic is 37. So it's the difference here is between a prediction or an estimate and the actual reality. Notice how I'm not talking about all voters, like all people who can vote. Because frankly, I only care about the people that do vote. And that's how politicians work. They're going to care about the people that come out to vote. So if you notice here, we have P hat for your statistic. You have P for your parameter. You don't need to write is a parameter, is a statistic. If you use the proper notation, that's all you need. So if I'm looking at B, what is a parameter? Which ones of those are parameters? 128 and 15. Because that's what I believe is true about everybody. But then they tell me that I have a sample of only 72 executives. That's my sample size. So the number that comes from that is my statistic, sample statistic. So when we're talking about parameters, mu is your average. 128 was mu. That lowercase sigma was also a parameter, standard deviation. And then x bar, or y bar, or whatever you wanted to use there. Maybe you used b bar for blood pressure, or p bar for pressure, whatever. That's what we're looking at. From here on out, it is going to be extremely important which one of those notations that you use. I mean, like, crucial. I'm saying you use P instead of P hat, you're down from a 5 to a 4 automatically. Okay? It's very important because this class is about being able to differentiate between what comes from a sample and what's actually true about a population. And so the notation is a key factor in that. All right. So what we could do here is I could take every single sample possible. And for each one of those, whether it's a proportion or a mean, our very first set of problems that we did averages. If I was going to talk about proportion, that would look a little bit different. So this would be my proportion. This is my population distribution. So if I've got chips in a bag. Some of them are blue, some of them are red. It's actually a 50-50 split. This is what's actually true. I can take a simple random sample, and here we have 3 simple random samples of size 20, and I'm going to show you what I get for each of those simple random samples. I get a proportion. My proportion goes from 0.4, 0.55, 0.65, so I've got a variable here of what each of those could be. And you notice that none of these look exactly like what's actually true. But if I were to take every single, or actually for this case, this was, I think they did a total of what was it? I think that was like 100 samples here. And this was their proportion distributions for 100 samples. So most of their samples, if you look at this, had averages right around 0.5, which is what you would expect to see, right? But you had some really crazy ones. We had one out here that was 0.15. We had one over here that was 0.8. And that's a huge difference. Because there are those samples that are just crazy. Oh my gosh, my hand is a magnet for just the blue chips. I don't know why. It seems to happen. For some reason, I go like, what are those snack mixes of all the different kind of trail mix type things? And I always grab the one I didn't want, and I keep pulling it out, and I keep pulling it out. I never get the one that I want. Yeah, Starburst. I happen to really like the one that everybody else hates, so I love the yellow and the orange. And I never get that. I'm like, I don't want that one. So a sampling distribution, what that is the, wait for it, this is like so hard to kind of pull together. A sampling distribution is the distribution of all possible samples. I know, right? The sampling distribution is if I were to take every single sample, what would all the possible statistics distribute like? All right. So in order to be able to do that, oh my goodness, chips but not chips. Yeah, I'm hungry now, but it's not that kind of chip. So go ahead and read this problem. Identify the population, the parameter, the sample, and the statistic. I was like, I think somebody's following me. Because they were. All right, what is the population? What is the population? Who am I interested in learning about here? The population is the 200 chips. The sample is going to be what? The 20 chips that we actually choose. So if the population is the 200 chips, what is my parameter? 100 red chips, but it's not just the 100 red chips. What am I trying to measure here? Am I talking about an average or a proportion? A proportion. So what should my parameter be? Half, 100 out of 20, 100 out of 200, sorry, 20 is weird. 50%, any of those are good. What is my statistic? The 7 out of 20. And that's what you really have to be very careful about. The population itself is the 200 chips. But when I'm talking about a parameter and a sample, those are the things that I'm measuring. I'm not measuring a count here, I'm measuring a proportion. So my parameter, which is P, is 100 out of 200, 0.5. P hat is 7 out of 20, which is 0.35. So what would I consider my evidence that less than half the chips in the bag are red? It's kind of a weird thing. Don't overthink it too much. Do I have any evidence that less than half the chips in the bag are red? So it says half the bag is red, but we have some evidence that that's not true. Like I can tell you anything I want. I could tell you my average SAT, my average AP score for AP statistics is 4.2. Just because I said it don't make it true. Do you understand what I'm talking about here? So I do have some evidence here that that's not actually the case. My evidence is the fact that in my sample, I only had 7 out of 20. That's not half. That's saying that in the extreme long run, we would expect it to average out. But what you have to do here is you have to understand that this is a claim. I was looking for that word. This is a claim. People make claims left and right. Just because I say it doesn't mean it's true. I'm a French model. Billionaire. Engaged to Elon Musk. Yeah, just because I said it don't mean it's true. Except for the French model part, because that's absolutely true. Hair flip. Glorious. Yes. Je m'appelle Frank. It's an old commercial. I don't know if you guys know what I'm talking about. It's really funny. Okay, so what we're talking about here is there's actual theoretical probability, which says that if I have 200 chips and 100 of them are red, then in the long run, it should be a 50-50% chance. That's if I know what's actually going on. But in statistics, we don't usually know exactly what's going on. So we're going to take our smaller sample to either kind of support or contradict a claim. So she claimed it was 50-50. My sample said 7 out of 20. That's not 50-50. That's evidence that that claim was wrong. Okay? So what we have here is this is a graph of 500. Sorry that this was 500, not 100. This is 500 samples of size 20. Now, if I have 200 chips, there are more than 500 possible combinations of 20 chips from there. So this is just 500 of them. So I want you to go through and read 4 and 5. Try to answer those. This is what statistics is about. It's about going from a sample to make an educated guess about the whole population. Four is trying to talk about context here. So that one dot at 0.8. What do you think that means? What does that one dot represent? (16 out of 20), because 0.8, when we're talking about that for a sample of 20, means that I had a sample where 16 out of the 20 were red. Each one of those dots represents a sample. And so that one dot represents the sample that I had 16 out of 20 chips that were red. So for part A, it kind of goes back to what we were doing for the previous, 5A goes back to the problems that we were talking about before. It said, would it be surprising to get a sample proportion of p hat equals 0.35? So 0.35 is here when the proportion is actually 0.5. Would you be surprised at something here? What do you think? You haven't dealt with this before, so yes? Okay, so one more time. You would not be surprised, but it's not really what you were expecting. Very good. Why would you say that?
Well, because there's been all these trials multiple times where that has happened.
Exactly. That's it. That's all I'm going for here. Is it what I was expecting to occur? No. It's not right there in the middle. But is it something that I would write home about and go, oh my God, they're totally lying. This is horrible. Probably not. Because, look at all of these other times where it was less than or even equal to that value. There are quite a few. So that's really all I was going for. I want you to kind of start thinking about this. We had several times where that 35% or less occurred. What else do we have that we've talked about marks whether or not something is surprising? How could we answer that is it surprising question? Whether it's 5% rare or less. What else? Okay, the distribution thing, the normal CDF thing. Okay, that's the 5%. What about standard deviations? 2. More than 2 standard deviations away, which typically ties to that 5%. So this here, we have, it's like 35%. That's not even close to 5%. So I wouldn't really be too shocked. It wouldn't be enough to me to go, that woman's lying. It says, based on your previous answers, is there convincing evidence that less than half of the chips in the large bag are red? Would you have enough evidence to go out there and convict your teacher of lying? Not really. Because that happened purely by chance. That 35% here, there's a lot of them. It's definitely bigger than a 5% chance of that occurring. So although it might not be what I expected, it's not really something that's crazy. So seriously, that was like the perfect way to describe that. So thank you. Yes, very good. She's like, this is weird. And this is what we're talking about. We're going to have claims, and then we're going to look at the evidence that we're given and say, is this enough evidence to mark that claim wrong? You guys heard about something called, a trial? Never heard of it. Never heard of the saying, innocent until proven guilty? What we're looking at here is, do I have enough evidence to say that somebody is not guilty? Do I have enough to say that this is too random, too rare to occur by chance? So, really cool little app. What we can do here is we're going to look at a whole bunch of different actual populations and use that to draw samples, graph the results, and compare the results. So, here we go. Let's do this and then this. Oh, why aren't you pulling up? Here we go. So this is just a cool little app that lets you actually do different distributions. So here I have an actual population. So this is everybody that I'm interested in. What would the number from a population give me? Is that a parameter or a statistic? What is that? Populations have parameters. And my parameters for this population, I have a mean of 16, an average of 16, standard deviation of 5. It's not skewed. Don't worry about kurtosis. So what I'm doing here is I'm going to take a sample of size 5. This is what my sample consisted of. And for that, you can take other samples. Hang on, let's do this. So this is one sample. That is the average of that sample. That is another sample. That is the average of that one. Another sample and its average. So I could do this for forever. Okay? So what I'm going to do here now is, if I were to do 100,000 samples. Look at all this. I'm making more and more and more and more and more samples. My average is extremely close, but my standard deviation is significantly different. Okay? So if I were to do some random crazy population. It says for this crazy looking population, my average is 14.7, my median 12.5, standard deviation, so I have all of my data points here. Okay? Nope, I can't do it. There we go. I can take a sample. There's the average. Do you see how each of these samples are starting to go kind of, even though the individual samples follow what the population is, the more and more samples that I do, if you look here, my average is getting a little bit better, a little bit more accurate. If I take a sample of 10,000 of those, another 10,000, 100,000, what's happening to my graph? My graph is becoming, you see that curve that I just threw in there? More and more normal. If I increase my sample size, now my sample size is going to be 20. So that means now I'm taking 20 of these little boxes. That's the sample average. Here's another 20. Each sample will follow the distribution of the original population. But when I start taking multiple samples here, going up to 10,000, 100,000, my sample starts looking, my distribution of all possible samples gets extremely normal. Okay? It doesn't matter what kind of a distribution I'd start with. Whatever you start with, one sample should pretty closely follow the distribution of what your actual population was. But when we start looking at all of the possible samples that we get from that, the more samples I take, the more normal my distribution should be. So if we look at here a sample of 20 versus a sample of 5, you can see here that the differences are a little bit obvious. When I go up to 10,000, the sample of 20 is definitely more normal than the sample of 5. When I start getting bigger and bigger and bigger, they start fitting a little bit better. Do you understand what I'm talking about here? What this gets us to is actually the whole goal for this. And that is, when we're describing the distribution of all possible samples. So remember, the top one was the actual population. Actual population can be wonky as heck. Really, really weird looking, totally random. But when I start pulling all samples from that, the center of my sampling distribution is called an unbiased estimator if it's equal to what the actual truth was. Okay, so here was our graph again. This is the sampling distribution for the proportion of heads for what we had before. Again, an unbiased estimator is if you have a value that's extremely close to what the truth was. So which of those do you think would be the best and most unbiased estimator for the actual proportion of reds in that bag? C? C is definitely the best. Which one do you think is the worst estimator? B, because it's the furthest one off. So that one's no good. When we start getting to values that are a little bit closer, like 0.47, we could actually consider that to be an unbiased estimator because it's fairly close. Okay, an unbiased estimator is something that you'd be pretty surprised about. So again, what does this one dot here represent at 0.15? What's that represent? 3 out of 20. That represents the one sample where we had 3 out of 20 that were red. So when we describe sampling distributions, and remember, this is not the actual population. The population can be anything crazy. What we want to see is as low of a spread as humanly possible, because that means we have better predictability. that means that our predictions are what we call trustworthy. I can rely on them because I'm starting with something that's going to be an unbiased estimator. So just because my estimator is unbiased doesn't mean that your statistic will be really close, because here what we have is these are two different sample sizes for the same problem. This is a sample of 100, and this is what my spread works out to be. Based off of this guy, I would say that my actual average here is probably at about 0.37 on both of these, 0.37. But which one of those do you think has a better predictability of having a sample that's accurate? A sample of size 100 or a sample of size 1000? Sample of 1000 is actually better. This sample of 1000 has greater predictability because you're not going to have that crazy little guy out here at 0.22. I'm not as likely to have that 0.52. You see, that's not possible here. The larger the sample means you have to take a whole bunch of different values. And if I've got 1,000 values, I can't find 1,000 values that are all going to be up here. The larger the sample, the more I have to take of those lower values, which is going to pull my average closer towards what it actually is. So you can have an unbiased estimator, but you still want as large of a sample as possible to reduce your variability. So we have rules that we're going to be using in order to apply this stuff. And it all kind of comes down to the spread of my data. And it says that the statistic has a spread that decreases as your sample size increases. So that might be an important thing to note. Spread, what's another word for spread? Range, what's another word? Range we don't always like because it's so susceptible to outliers. One more time. IQR is good if we're looking at, sorry, I got something on Apple, is good if you got something that you know is skewed. What is another measurement for spread? Standard deviation. One more. Variation. And generally when we're talking about spread, we use the term variability. So we're going to say we have less variability with a larger sample size. Bigger is better here. So I really don't care about how big the population is. Doesn't matter. What I care about is how big my sample is. So you might say, okay, so how many people are there in the US? Is he right? I have no idea. Okay. About 330 million. That's a freaking huge population, right? If I took a sample of 10,000 people, do you think that that would give me a good estimate for the population? 330 billion people in the US. Million, I was going to say that's a lot. Dear Lord. 330 million people in the US. I take a sample of 10,000. Do you think that will be representative? I don't care about the proportion. I care about the sample size. Is 10,000 a large sample size? Yes. Is 50 a large sample size? Probably not in this case here. Depends upon what we're talking about distribution-wise. Bigger is better. It doesn't matter what the size of your population is. Do not think about the fact that, hey, a sample of 100 is always better than a sample of 10. That's true. But don't think 10% of the population is always better than a sample of 2%. We're not talking about percents, and actually we have a little cutoff where we can't go bigger. So you got to be very careful. The variability is described by the spread, and that's going to be determined by the size of your sample. Larger samples, smaller spreads, and then here's kind of our bottom line here. The spread of a sampling distribution does not depend on the size of the population. But your sample cannot be bigger than 10% of your population. So even though we have 330 million, not billion, people in the United States, I could not take a sample of 100 million. That would be bad, because that's more than 10% of the population. Because the folks that you are not getting to are going to have some sort of common trait. There's going to be a reason why you don't have these people. It's a lot harder to be absolutely representative if you go over 10%, because you're going to say, it's the idea of drawing without replacement. The probability of being selected, if I have a group of 100 people, the first few people are going to have pretty similar chances of being selected. But once I get past that 10th person, since I'm drawing without replacement, that probability is now changing significantly enough to where the next person does not have the same chance of being selected as the first person did. Okay? All right. So it's very important here. Your population, you can think about it two different ways. Either your sample has to be less than 10% of your population, or your population has to be bigger than 10 times your sample. Okay. Go ahead and give this problem a shot. So for this problem, what is the parameter that I'm trying to figure out? Guys, what is the parameter? Find a percent or proportion of what? Of what? What am I trying to learn about? Residents? Okay, in community. But what is my number that I walk away from going to be representing? As irritating and obnoxious as it is, and as monotone as he said that, he was correct. The parameter here, what we're trying to learn about, is the actual percentage of residents who would answer yes to, do you know the name of at least 5 other people who live on your block? This is context, ladies and gentlemen. What is the statistic? Okay, the statistic is going to be the actual number that you get from your sample of 100. Okay, this is about context. The parameter is the proportion of the people in the entire community, being very specific here, who would answer yes to the question, and our parameter here is 0.4. The statistic is those in my sample of 100 that actually say yes. Do you understand the difference here? One is what's actually true about my entire community. The other one is what did I get from my sample of 100. What do you think the sampling distribution, when we're talking about a sampling distribution, what does that describe? Sampling distribution. The distribution of the samples? I need more context than that. Random sample, okay. I need more context. I don't have any context in what anybody said. There you go. Need a little more. The sampling distribution is all the distributions, describes the distribution of the proportion of people who would answer yes to this question. What's important here is you have to continually note the sample size, because your sampling distribution is going to change based on your sample size. So the sampling distribution describes the proportion of people who would answer yes in all possible samples of 100. Context. We're going really, with the probability unit that we had, context wasn't quite as huge because it was just asking you probabilities. Now we're going back to that idea of context, which means that's going to be another struggling point. If I were to say that my statistic in this case was an unbiased estimator, what would that mean? What does an unbiased estimator do? the sample properly represents the population. Or we would say the mean of the sample is equal to the mean of the population. That's unbiased, means it's a good representation. It reflects, it equals. Does that make sense? Meh. Itty bitty witty bitty bit. Oh, make senses. Dad stat joke. There you go. Okay, just a little bit more to finish this off. I want you guys to try D and E. We really are almost at the end. Bye, ladies. You remember test tomorrow. Or next class. Tomorrow? What flex is tomorrow? 5-7. Well, at least you didn't say 1, 2. That's the worst flex. It's the second worst. Okay. All right, guys, come on. Let's finish this up. Not that much left. Your brains are already melting. Melting. What have I changed for D? The population size. And I've made it what? Bigger. What does the size of the population have to deal with the sampling distribution? Say it again. Nothing. As long as bingo, bango, bongo. Absolutely. Shouldn't change a darn thing. As long as the sample that we take here, which is still the 100, it shouldn't affect the sampling distribution at all, as long as we stay under that 10% mark. But hey, if my original sample was okay, and now my population is larger, my sample should still be okay. So for D, we were talking about changing the actual size of the population, which we said has no effect. For E, I'm changing the size of the sample. So of my sampling distribution, when I'm describing a distribution, what do I use to describe? What are my 4 things that I have to talk about? Shape, center, spread, unusual features, or outliers. Is my shape going to change? Not really. It should get more normal, because remember, bigger is better when we talk about sample sizes. Should my center change? No. If we think back to the very first thing that we did today, sample of size 2 versus sample of size 3, my average stayed the same. Spread. Spread will change. If I'm going to take 50 instead of 100, what will my spread do? Spread will get bigger because I've taken a smaller sample. Bigger is better, smaller is not good. Okay, so just a little bit to finish this up. When we're talking about statistics, it's kind of like a target. I want my statistics to hit the bullseye. I want my sample to be beautiful. This is a perfect sample. Accurate and low variability. Like a census. Well, census would cover the whole thing, but yeah. However, if you look here, I still have that low variability. I have a tight cluster, but it's high bias. It's not even close to the target. This is low bias, so we are still centered around the target. Big spread, high variability. This is just horrible. That's high bias, it's not even close to average, and a big spread. So bias, when we're talking about bias, our aim is off. I'm not getting that target that I want. There's something that's pulling it away. And high variability, okay, is all that stuff. Good, we're good. Real quick. Yep. 3 FRQs. Yep. Thank you, guys.